everybody. This model video is going to cover Model 7, which is a moderated mediation or mediated moderation effect using Andrew Hayes' process macro for SPSS. So don't forget that you can look up what all of the different templates are and the different models and how they work. So it's templates.pdf. It's included as part of the download for process. And so what I did is I've pulled up that template and I'm looking at Model 7, which is a simple mediation model with a moderator here between X and M. Now Model 7, 8, 9, what happens is they just add more complicated moderation, and then at some point after it goes through all the different moderations from X to M, it changes from M to Y and then sometimes only X to Y. So a lot of these different model numbers really focus on where the moderation occurs for moderated mediation. And so we're just going to cover Model 7. It's probably one of the most popular, and it's been one of the most requested things for my YouTube channel. So what I've done is I've taken that model and I've let me just close this, made up an example for it. This is very similar to my example for Model 6. Where I have some faculty evals that we use to measure our courses, and we're just looking at how they're affected by different questions. So I want to know how professors are rated, so I'm using that as Y. So what predicts my rating in the course? What I've found, especially when you teach statistics, is that if it's a course they wanted to take versus a course they were required to take, it heavily impacts your ratings. So our statistics and research methods classes tend to have lower ratings because they don't want to take it, and even though they're required to, whereas we have a really popular sexuality class, also taught by a great professor, but people really want to take that course, so the ratings are much higher. And the professor's awesome. But what if wanting to take the course is moderated by the grade that mediated here, this M, by the grade you think you're making. So I don't want to take this course, but I'm making a good grade, so all right, I'll give the professor a better score. So it might be that the wanted to take is also kind of affected by the grade they think they're getting in the class. So maybe you really wanted to take this course, but it turned out to be really hard and you're making an F, and so now you think the professor's awful. But that relationship between I wanted to take this course and the grade I think I'm making might be moderated by whether or not I think the grading system is fair. And so that actually moderation might occur over here on this B path as well, between grading and rating, where if the grading I think is fair, that affects this rating. But we're sticking it over here just to show you Model 7, so maybe there's a moderation here of different relationships between I wanted to take this course and the grade I think I'm making based on whether or not I think the grading is fair. I don't have the best data set for this example because I find these data sets kind of hard to make up. So this moderation is not going to be significant, but it will still show you how to run one of these models and interpret the output for them, which is the most important part about these videos. So I've got each of the paths labeled except A over here because A is actually going to be 3 paths. So we'll have a path from X to M for a average group that would be right on the mean for the group because we're going to mean center. A low group, which is 1 standard deviation below the mean, and a high group, which is 1 standard deviation above the mean. So it would take sort of the average amount of grading, we're going to look at the average amount of fair grades here and see what the relationship between wanted to take and grading is, and then look at 1 standard deviation above and 1 standard deviation below, which is very normal for moderation analyses. For me, one reason why I really love process and SPSS is it does all the dirty work of mean centering and creating those simple slopes for me. Now, if it were only do data screening and power, that would be great, but one person can't do everything. We're also going to look at B, C, and C prime. One thing that this analysis will also give you is the overall mediated moderation effect, which is sort of like an overall effect that this having this path here is, so the overall mediation effect, but also including the fact that there are 3 different paths from X to M. And so I find it helpful to look at those templates because for me, I'm much more visual. I like this version better, and it allows me to see what it is I'm actually doing when running one of these models. All right, in my last video, I actually forgot power, but we're going to try power on this one. And so I love GPower. It's fantastic. It's clickable. And so it'll let you sort of hack a way to do this. Now, there are better, more precise ways to do this, but really, if you're trying to do a priori sample size estimation, you just really need a best guess. And so what we're going to do is we're just going to use GPower in a traditional regression analysis and give it our best guess. So I'm going to click t-test here and change that to f-test because regression is an f-test. Under statistical test here, I'm going to go down and change that to, you can pick either one here, but fixed model R-squared deviation from 0 is probably the easiest one. And what I want to do is figure out if I'm predicting y in that final model, so the last model that predicts y, how many predictors do I have in the model? Additionally, what would I expect R-squared to be? Because overall, you're trying to predict y. Now, you think x predicts y, and you think m predicts y, but you really think x predicts m, which predicts y. So m should take the brunt of the R-squared here. And then there'll be some other effects due to the fact that w is included in this equation. But in reality, I'm just trying to figure out like how much R-squared of y am I trying to get? Because if none of them predict y, then this is a useless analysis. Oh, I meant to leave that templates thing open. Let's open that back up. So templates, PDF, there we go. Now, if you aren't good at guessing how many predictors you have, what you can do is come down here to model 7, if I can get there. Oh, that's 6. A couple different versions of 6 here. Oops, there's 7. So for 7, what we've got is actually a couple of different predictors. But in the final model, what we're really going to have is x and m only. So w only really enters the picture when we have a step that's looking at x to m. So w actually isn't in the final model. It's just x and m. And so if you aren't sure, you can also run the analysis, just like a fake one real quick, and look at what is in that model that's predicting y that we want the biggest effect for. So we're just going to have x and m predicting y, but then again, w is going to be in there somewhere. So if you aren't familiar with these types of models, we're just going to try to run real quick and look at the final step. And I've got this all set up. I'm going to show you how to set this up in just a second. And so the purpose of sort of running a fake analysis is just to see how many predictors there are, just so that you know that you're doing this step correctly. And I do have a lot of data points, so it does run kind of slow. Okay, here we go. Now, the last model is the model that's going to predict y. Okay? But what's happening is, look, so we only have x and we only have m. Because the W effect only occurs when I have x predicting m. So really, for power-wise, when I'm trying to get at R-squared, it's really just x and m. Okay. Now this is really a hack at predicting sample size. There are definitely more precise ways to do it. I would recommend looking into R, and because those there are some packages that make it easier. So click determine, and what effect size do we expect to find? Well, if you want to use traditional standards, you can either use 0.01 for small, 0.06 for medium, and 0.14 for large, for R-squared. I've always gone with just squaring Cohen's R ones, which would be 0.01, 0.09, and 0.25. It kind of depends on which train of thought you're with on these. But let's say we know it's a large effect, so I'm going to do 0.25. Now I'm going to hit calculate and transfer to main. And I did that because I tend to work in R-squared, I don't tend to work in F-squared. So F-squared is not a statistic that Psych tends to use very often. So I need to convert. For alpha, I'm going to use 0.05, that's standard. For power, I'm going to use 0.8. And my number of predictors is actually only 2, x and m. So it says with a large effect size, I need 33 people to achieve 80% power. If I lowered that effect size, I say, well, maybe I don't think it's actually large, maybe it's medium, 0.09. Calculate and transfer to main. It would say I would need 115 people. Sometimes if people tell me they aren't sure, I tell them to estimate small and medium and take the average. So kind of a halfway between the effect. It's always good to overestimate the number of participants that you need so that your studies are not underpowered. Okay, so that's just kind of a cheat way to get an estimate that doesn't involve just a whole lot of math. Okay, so let me close this so we don't get tempted to look at it. What we're going to do now is talk about assumption checks. Now there are lots of ways to do this as well. And probably the most accurate way would involve using a lot of the interactions to predict, included in the brain fart, sorry. We include the interactions in this analysis, but remember that last step is just X and M, but we really also need to screen W here. So what I'm going to do is kind of take and not use the traditional regression data screening. Now, if you've watched a lot of my videos, this will be familiar because this is the same process I tend to use on all of them, where I'm just going to screen all 4 variables, sort of assuming that they're all going to get used in some way. And I like to do this analysis because it lets me handle all of the variables instead of just in mediation, you're working with different DVs. So sometimes the DV is Y and sometimes it's M, and this allows me to check all of them at once. Additionally, it also allows me to check W, considering it's only used in one of the analyses, one of the steps, rather. Okay, so we're going to screen everything. We're going to use our cutoff criteria as p less than 0.001 as a scary sort of number that we would need to fix because we want our data to be really, really crazy before we start doing anything to it. That's the rules from Tabachnik and Fidel. A lot of these ideas are also stolen from Andy Field, but I know he talks about 0.05 in his book, but we use 0.001 in my research lab. Okay. So to start, the first thing I'm going to do is to check that the data is accurate. So we're going to do analyze, descriptives, frequencies, and these are all continuous variables, so I'm going to move them all over. Turn off display frequency tables. Because these are continuous, I will give me a ton of decimals in these big tables I don't need. Under statistics, I'm going to ask for the mean, the min and the max, and the standard deviation. I could also look at skew and kurtosis for each individual one to talk about normality. I also have 3,000 data points, so I'm well over the minimum for normality. But instead, I'm going to check multivariate normality. And then hit OK. So I don't have any missing data. That's fantastic. I don't have to estimate any missing data. I can look at the means here. Now this is a 5-point scale. It ranges from 1 to 5, so these are going to be skewed because they're biased towards the top. But I'm not too surprised by these means. They tend to average around 4, which means I guess our students like us here. Our standard deviation is usually about 0.5 point for this scale, so none of these seem too small or too large. And then our min and our max do not go outside the range of the scale, which is 1 to 5. And that's one of the most important things, is making sure you don't have out-of-range data. If you're using any kind of scale that requires reverse coding, you could also notice that here, because the mean would be much smaller than expected. Or you can use frequency tables to realize that the data looks kind of backwards. Which happened to me recently, where I didn't realize that something was wasn't reverse coded until I pulled up a frequency table of the means. So everything looks fairly accurate. I don't have to deal with missing data. Now we're going to talk about outliers. So for outliers here, what I'm going to do is check using Mahalanobis distance, which will give me a mean of all the means and see how far away people's scores are from that. So if I'm looking at the distance of someone's points from the centroid, or the center of the center, I can tell if their pattern of data is odd. And that's one reason why I really like Mahalanobis, is because it lets me look at their patterns of scores rather than each score individually, where you could have someone be an outlier on, let's say, W, but not M, and so what do you do with them? Because any missing data point throws them completely out of the analysis. And in this case, this would let me see if patterns are odd for a participant. That's especially useful if you're using any kind of scale data where you have lots of questions and people go in and make pretty scores on their Scantron sheets, and that's not what you're wanting. But to do that, and to be able to get all of these, the next piece on assumptions, we're going to make up some fake data. So we're going to make up a random data column to predict, and then therefore, if we're predicting a random data column, at least the residuals should be random, which is part of our assumptions checks. And so I'm going to transform, compute variable, and I'm going to call it random. Under numeric expression, I'm just going to click, but I'm actually going to go over here to function group and go down to R for random numbers and pick RV chi-square. So we're picking a random variable out of the chi-square distribution because at least Mahalanobis and our unstandardized residuals are chi-square distributed, where we should have lots of small ones and only a couple of large ones. Lots of things close to 0 anyway. And so we're going to pick a number here for degrees of freedom, and I'm going to pick 7 because it's just kind of a magic number. It works. There's no particular reason why 7 over any other number, except that it has always worked for me. Don't pick anything too small, like 1 or 2. You won't get enough variance here. So click OK. And what that's done is it's given us a random number. Now this, I will warn you, is not random at all. It always gives you the same pattern of random numbers if you pick 7. So if you're following along, it actually will give you the same pattern it gave me because it's not random. If you use another program like R, it does give you random numbers. Okay, so SPSS's random number is based on a set seed. So it gives me the same random numbers every time, which isn't totally random, but it works well enough. Okay. All right, so to get Mahalanobis, we're going to do Analyze, Regression, Linear. We made that random number for a reason, so we're going to put random in our DV box. And all 4 of these in our IV box. Okay. And that means we're going to have 4 independent variables, which will be important in a second. Under plots, Z predicted in Y, Z residual in X. This will give us our residual scatter plot for homogeneity and homoscedasticity. Click histogram to get your normality histogram and your normality probability plot to get your PP, sometimes called a QQ plot, for linearity. Click continue. Under save, click Mahalanobis. Now, if we were doing a real regression analysis, I would use Cook's and Leverage, but since this is a fake regression analysis, because we're predicting a random variable, I'm just going to look at Mahal. Click OK. I'm going to get a lot of output here. I'm going to click the fancy star button to go back to the data. So I've got my Mahalanobis scores out here. So you can right-click and sort on the data, but for some reason that doesn't always work on a Mac laptop. So I'm going to go Data, Sort Cases. I want Mahalanobis descending because it's always positive, so that's helpful. So I got some big scores out here. So look at this first participant, and this is what I mean about the pattern of scores. So individually, these scores would not have come up probably under an outlier, except maybe X here. So for X, they really hated the course. This is the course I wanted to take. But then they gave everything else very, very good scores. Now these are averages across the course. So this is like an entire course, each line instead of each participant. But that way, so we don't have problems with independence here. But that's a little unusual, and that's probably a typo or there's something wrong here. But if you look at the next line, it's a completely different pattern of data. That would not have come up under z-scores as outliers given the standard deviations. More than likely would not. Maybe these two down here, these low scores. But it's really odd for the person to, this is a course I really wanted to take, but I hated it so much and it was awful. Okay, that's actually probably happened before, but the patterns are odd. So what do I do with this Mahalanobis column? Well, you're going to need a chi-square table. See if I can find mine here. Here we go. And I'm going to use 4 degrees of freedom. Now, degrees of freedom has nothing to do with n here. It's the number of variables you put in that independence box. So I have x, m, y, and w. And we're going to use p less than 0.001 as our big important rule. So 1847 is our cutoff. So we have a lot of people over 1847 here. And what I could do is delete every one, so it'd be 58 outliers above that score. Okay. So what I would want to do is save this data set as something else, as no outliers, so that I don't forget later that I have deleted these outliers. So I kind of have a couple of saved files that include any fixes or changes that I did to the data set. So when I go to write this up, I have the original file, and I also have files that remind me of what I did, because there's often a big delay between when you're running an analysis and publication and reviews. There's not often a big delay, there is a big delay. So let's get rid of these people, because their scores, or pattern of scores, is creates them, they're an outlier. Now I could leave them in because this is real data with real professors, but that does not mean that the data is perfect because it had to be entered by people. So I could also assume that maybe some of those data points were incorrect or inaccurate. While they still fell within the line of expected scores, maybe they just got entered incorrectly. All right, so now that I've checked the data for outliers, I'm going to have to rerun that assumptions analysis, because I've deleted people. So now those pictures include people that I've deleted. So go Analyze, Regression, Linear. It's also set up correctly, so I'm going to hit OK. I will get, kind of hide that one for myself, I will get another Mahalanobis column, but I don't really want to look at it, because you don't want to delete people twice, so you only delete once. So let's go back. So the first chart you're going to see is a bunch of stuff you don't want to look at. So we're going to look at the pictures only, and we're going to look at the histogram of the residuals. Okay, now these residuals should be mostly centered around 0, because this is a random thing. So we're in predicting a random variable. Mostly you should be kind of on either side of 2 standard deviations of 0. So these are standardized. So that makes it normal. Remember that chi-square distributions are positive, but these are residuals, and they're standardized residuals. So it's the distance away from the line that we're getting, so that kind of makes it normal. I do have a little bit of positive skew out here, but most of the data is between 2 and 2 and really hovering over 0. So maybe a slight positive skew for normality. But I also know that I have 3,000 participants, so I'm not too concerned because it's fairly robust to violations of normality. Linearity is all right. It's not fantastic. This should be a little bit closer to the line, but remember about the squint test, if you will, if you've watched several videos, that's close enough. So it's not bowing too bad. And now this is actually really not pleasant. So we want to look at a line here at 0, both vertical and horizontal. So for homogeneity, what we're looking for is the dots to be centered around 0, and they aren't at all. So this runs from 2 to -4 and 2 to 6. So this is not homogeneic. So each variable has a fairly different variance range. And one issue with that is it's sensitive to sample size, because with really large samples, any difference in standard deviation can be significant, which is one reason why you don't tend to look at tests like Levene's or boxes, because they'll be significant with large sample sizes. But this indicates that we might have some issues with homogeneity. And in a perfect world, I would stop and run this analysis using potentially a non-parametric regression style analysis, but the purpose of this video is to show you process, so we're going to keep going. If I look at homogeneity, I would say this is bad. If I were looking at homoskedasticity, I would draw a line around the dots and see if I just had a big blob. Because remember, we're predicting a random variable, so these dots should appear in a fairly random pattern. But I would argue that I don't have that. I have a fairly nice Dorito chip, or what would be a good example of this? My students draw me silly pictures every year, which I truly enjoy. I have one student right now who is just fantastic at drawing superhero pictures for me. This kind of, to me, looks like a street light that all the bugs are attracted to, or potentially a flying V UFO, but it certainly is not a random blob of dots. So homoscedasticity is going to be problematic. And what we're going to really have problems with is predicting the residuals for some of our extreme cases. All right, so the data screening on this analysis is a little iffy. But let me show you how process works. So if your data screening goes fine, you can still use process. All right. So what we're going to do now is actually run the analysis. So analyze, regression, and process. If you don't know how to install this plugin, you should look at Hayes' website. He explains it. There's also a how-to with the download. I'm going to hit reset just so you can watch. Okay. You're going to stick Y in the outcome variable box. Okay, oh, well, you're going to, maybe we're going to start with X. There we go. So I'm going to put X in my X variable box, Y and Y. M here, so I don't want multiple mediators. I'm going to put Y, or W, sorry, down here in my moderator box. If you have other variables you want to covary out or control for, you can stick them here in covariance. We're going to pick model 7 here. Under options, I'm going to choose mean center for products so that my W variable and X will be mean centered, which just means that it's going to take the average score for those and subtract them from every variable, which makes 0 the average score. It's a very, very good way to be able to understand the simple slopes. Heteroscedastic consistent standard errors are great as well. And unfortunately, none of the cool options for plotting or the mediation effects are available for this model, so we're just not going to click any of these because they won't come out anyway. So continue. Under conditioning, though, if you want to change from mean centering and getting plus minus 1 standard deviation to percentiles, you could. I've always done low, medium, and high, sort of simple slopes, so I'm going to leave that, but don't forget you can change this and get percentiles instead. If any of your variables are categorical, at the moment you're out of luck because it only runs for models 1 and 4, and so you would need to hand dummy code those yourself, but if you're doing models 1 or 4, you can use this multi-categorical box, which is a fantastic new option. And if your variable names are long, I would click allow long variable names so you don't have to rename them. I've named mine what box they're going into just to make it easier for a teaching example. All right, so I'm gonna hit OK. And I'm gonna let that bad boy run. There we go. So let's look at this output we're getting. So it reminds you here what you've done in our very large sample size. And then it breaks it into 2 steps. So generally a mediation analysis involves, does X predict Y? Does X predict M? And then does X and M together predict Y? But part of this sort of leaves one of those steps out, but it includes it in a sort of a different place. So what we're going to do is just look at each piece here. So I'm going to look at the moderation component first and see what happens when I'm looking at X predicting M. Okay, so X individually predicting M, sort of ignoring or controlling for W, is significant. So it's 0.20. And so that would be our traditional A effect, except we've got some other variables in there. Now W also predicts M by quite a lot, so it's 0.68. So what we've got is X predicting M is significant and W predicting M is significant. What we really would hope would be significant, wherever that box went, there we go, is this interaction term here. Now, it is not significant because I said I didn't have very good data for this. But if we were looking at this and it was significant, we could use that information in a little bit. Okay. So X predicting M is our traditional A path, but what we're more interested in this type of analysis is that interaction being significant. And if it is, you would go down here to this conditional indirect effects and be able to look at each effect given X on Y at the different levels of our moderator. Okay. So what happens is W here gets broken into three pieces: low, we got low, average, and high for our M variable. And so this is the effect of X on Y at those different levels. Okay. What I want to do here, though, is look at predicting Y. So does X predict Y given M? So this is the sort of model with both predictors. So this is C prime here, and that's considered the direct effect of X on Y. So that is going to be 0.11. It is still significant. That doesn't necessarily rule out moderated mediation, although we didn't have any moderation, but okay, so we got 0.11. And if I wanted to write that up, I would say the t value is 4.88. I'm going to use this degree of freedom here, number 2, so 3524. And that was significant. Okay. So that would be APA style, and this here is B. This is unstandardized B. Okay. Now, M is also a significant predictor of Y. And so its coefficient is 1.03, and that's B over here. This is the B path and the B step in your sort of traditional Barron and Kinney rules. So B, is 3524. I think it was something like crazy, like 50. Where's B here? Yeah. 50.13, P less than 0.001. Okay. So those are both significant, which we kind of wish X wouldn't be, which would imply mediation. But instead what we want to do is kind of look at these several effects here for C. Okay. And so what this piece here is telling me is what is the indirect effect of X on Y at these different levels of moderation. And so what's happening is we're sort of getting 3 C's. So our mediator here is M. This W here indicates that it's 3 different levels of W, so a low, an average, and a high. And I think I actually have these labeled as A, and that's not what I meant to do. And so we're getting low, average, and high of their belief in fair grades. And we're looking at the effect here of X on Y. So it's a little confusing to read at first because there's kind of a lot of variables going on here. But it tells me which mediator it is, because you can have multiple mediators. It tells me what level of W we're working at, and what is the effect of X on Y. Okay, so that's why it says here the conditional indirect effects of X on Y at different levels of these different levels of the moderator. So this is a mediated moderation effect, okay, or moderated mediation. Okay, kitty cats should not have a fight while we're recording videos. All right. So what are these negative numbers? Well, 0 here is average. And this is 1 standard deviation below and 1 standard deviation above. So it's what makes it low, average, and high. And here are our C's. So this is why we're not seeing that interaction. So this interaction here is not significant because look at these simple slopes, effectively. They're not really different. Now they aren't simple slopes, because simple slopes actually would happen here, where we would look at each level of X predicting M given different levels of W, but they're sort of like simple indirect effect slopes, if you will. So it's kind of creating three different little mediations to see if there is moderated mediation. Okay. There is no moderation, so that's going to be kind of hard, but there still might be mediation. Okay. And you can see that there is maybe a little bit of mediation because look at these effects are different. The indirect effect is 0.21, the direct effect is 0.11, so that implies that there is at least something going on because there's a difference there. Now, I don't know if it's significant, mostly because I'm not testing that at the moment. I'm testing if the moderated mediation is significant. Right. So we got 0.21, 0.21, and 0.21, so clearly no moderation. Those should be different if moderated mediation occurred. Well, at least the moderation part. Okay. Now, I don't get t-values for these because they're not tested. If you wanted t-values, you'd have to do something else. But I do get these confidence intervals. So one way you could predict, you could talk about whether or not these were significantly different from 0 is report their confidence intervals. But at the moment, I don't know if I really I mean, I do care if it's significantly different from 0 because we want the indirect effect to be different from 0, implying that there's mediation. But to really test mediation, I have to compare the indirect and direct effects, right? Because I know the direct effect is different from 0. So at the moment, that doesn't really tell me if I have mediation. I need to compare these two directly. If I ran, let's say, model 4, model 4, I could see that there was a mediation effect. But you could report the confidence intervals here, one, just so that it's perfectly clear what they are, but also reporting that this is different from 0. But the kind of important piece here is this index of moderated mediation. So moderated mediation, what it does is it is telling me if these three effects are, one, different from each other, but also different from the direct effect. So the moderated point is that these three levels of sort of simple slopes are different, which I can tell you are not because this interaction is not significant. And then also they are different from the direct effect here. So in a perfect world, these three things would be different, and at least one of them would be different from the direct effect. Okay. And so it's this mediator here, it gives you sort of an index of that combined idea of the differences from each other and the differences from the direct effect, and then gives you its confidence interval. Now here's the big one. You do not want this confidence interval to cross 0. You don't want one side to be positive and another side to be negative, because that indicates that 0 is a valid or a probable value. And this particular one is, because like I said, I don't have the best example for this. And that implies that there is no moderated mediation. There might be mediation. Here it kind of looks like maybe I have some mediation because the indirect effect and the direct effect appear to be at least a little different. And I would need to test that separately. But here I definitely do not have moderated mediation where these are different from each other and different from the direct effect. And I could report that as I would report it as an index of moderated mediation. You can report this index value and its confidence interval. Because then I have a way to imply that it is different from, significantly different from 0, which is what we would want. So in this case, we don't really have, and you would also want to report the values for x to m, w to m, and x to x in the interaction. And so I would say that's traditionally would be considered A, but then we also have some other values in there that don't really have traditional labels. So let's see here, x to m, was significant. So if I wanted to show you how to report that, look, the DF is going to be different. So it's 3523 is 1407, and our P was less than 0.01. But then I would also want to report W to M. Oops. If I can type today, which is probably not, and then the interaction, predicting M, and talk about those. In this particular case, they're not significant. Well, W is significant, and we report it in the same way. So 3523 is 4615, and it is also significant. So we do, this is APA style, so I am technically a psychologist, mostly a statistician, so 4615. But there does not appear to be moderated mediation in this case because these B values are all the same. And so this is kind of a hack example of how to read the output of a process, how to run maybe some power and some data screening for this type of model, and then hopefully yours worked better than mine in this example. And feel free to ask questions if you have them on these types of models. The models that are presented after this, 8, 9, 10, 11, are all different places to put the moderator. Double moderated mediation, where you have 2 different places that you expect there to be interactions, and then adding even more moderators to the analyses, so they get more complicated real fast. But I hope this helps you out, and then you enjoy and look at the rest of the videos on my channel.